Thank you, Michaela, and welcome everyone to today's webinar. Today, I want to give a short introduction on Class D audio with post-filter feedback using MPS Axign technology. Now, let me see if my slides continue. There we go. So we start off with a small introduction, and then we'll get into post-filter feedback in Class D audio. Afterwards, we discuss fully digital feedback loop design, high-efficiency audio amplification, and I want to discuss the audio quality of MPS Axign systems. We'll round up with a small summary and conclusion. So without further ado, let's get into the introduction. So Axign is a fabless semiconductor company based in the Netherlands. Axign was founded in 2014, so we have a bit more than 10 years of experience in mixed signal design. And we have 2 locations in the Netherlands, the headquarters in Enschede and 1 location in Nijmegen, both on the German border. So Axign and MPS have had a long relationship, which is very logical due to the very complementary IP, where Axign has traditionally made the audio controllers and MPS makes a lot of standard analog IP, such as DC-DC converters and power stages. Axign was acquired by MPS at the beginning of 2024, and the reason for this acquisition is nicely captured in the official statement. So Axign is excited to announce that we are now part of Monolithic Power Systems. Our unique audio technology and expertise, coupled with MPS's manufacturing, product breadth, and system-level expertise, will enable us to offer industry-leading audio solutions without compromise. So for me personally, my name is Olaf van der Meer. I'm a business development manager at MPS Axign, and I have a background in Axign's applications and customer support team. So to start, let's quickly recap what is Class D audio. So we are dealing with switching audio amplifiers. We are taking an input signal, we feed it into a modulator, which then creates pulse width modulation or pulse density modulation. For the sake of this presentation, let's assume we are dealing with PWM, pulse width modulation. The switching waveform is then fed into a power stage, which amplifies it. And the amplified switching waveform is fed through a Class D output filter, sometimes called a reconstruction filter. Then we retrieve an amplified version of our original audio signal. So we are not just talking about Class D audio at MPS Axign, we talk about post-filter feedback in Class D audio. So post-filter feedback implies we take a feedback point behind the output filter. So in the second picture, we see a conventional topology where we take a feedback point in front of the filter. At MPS Axign, we take feedback behind the output filter. Now, the primary reason to use feedback is to suppress noise and distortion in the forward path. The forward path being everything between the input node and the output node. So this includes errors in the modulator, errors in the power stage. But when we're taking the feedback point behind the output filter, we are correcting for errors in the output filter as well. It should be noted that when using such feedback, the total harmonic distortion and noise in the feedback path cannot be corrected. In short, high quality feedback is key. We can only make corrections for errors in the forward path, but not that in the feedback path. So getting into fully digital feedback loop design. Why do we make it a fully digital feedback loop? So in the analog domain, parameter spread will always present a limitation. And when we are going to higher order feedback loops, meaning very aggressive feedback loops with a lot of noise shaping, we have smaller margins of stability. And when dealing with these smaller margins of stability, we cannot afford to deal with parameter spread. In contrast to analog loops, our digital feedback loops are consistent and programmable. So consistent implies we don't have production spread, and programmable means that we can easily configure these loops. The digital coefficients of our feedback loops are loaded on startup, and we can easily make an update for a different customer or a different project using the same architecture. An advantage of the programmable feedback loop is that we can fine-tune to, for example, certain performance requirements or for the lowest power dissipation. So this also makes it easy to meet specific targets. On the right, we see what this looks like. We take digital audio input, so no analog signal, Nowadays, most audio sources are digital anyway. We feed it into a digital loop filter. The loop filter determines what the feedback loop looks like and how it behaves. You can basically see this as making a lot of gain for audio band frequencies. We feed the signal into the PWM control, the pulse width modulator. The switching waveform exits the chip at typically 3 volts and goes to a power stage where it's amplified. The output signal over the speaker terminals is measured back and fed into the ADC as quickly as possible, so we are back in our digital domain. As mentioned before, ultimately, the quality of the feedback system is limited by the quality of the feedback path. So a high-resolution analog-to-digital converter, the ADC, is required. And this patented ADC technology is really a cornerstone of the MPS Axign technology solutions. So here we see how it works in a block diagram, but how does this look like in practice? So there are 2 products available right now, the AX5688 and the AX5689, which are a 2-channel and 4-channel controller respectively. These controllers can be used, for example, in conjunction with power stages and DC-DC available from MPS. So on the right, we see an example application where we could use the 4-channel controller AX5689, and we use 2 MP8049S power stages, which can both make 2 bridge-side load channels. So effectively, we have created a 4-channel audio system. It should be noted that the AX5688 and 5689 are power stage agnostic. So this means, in principle, these controllers can control all power stages and even motor drivers. So besides these products, many more MPS Axign products are in development. The best way to stay tuned on what is coming out is to visit our website and subscribe, and we will notify you as soon as possible when a new product is coming out. So moving on to high efficiency audio amplification. Traditionally, the move to Class D is fueled by the desire to have higher power efficiency. So for very high output powers, let's say close to 100% of the maximum output power of the amplifier, Class D amplifiers are known to have an efficiency easily around 90%. And this is a great leap forward compared to the Class AB amplifiers. However, if we consider typical audio content, we see that about 70% of the audio signal is between 10 and 40% of the maximum output power. Of course, this depends on the exact type of music, but this is just a rule of thumb. So the losses at normal listening levels are largely determined by switching losses and ripple losses. The first category, switching losses, largely occur due to parasitic capacitance charging and depleting every time we switch our power stage. And the ripple currents, they run through the power stage and output filter inductors, and they're an artifact of having a switching amplifier. It should be noted that in traditional Class D amplifiers, the maximum ripple occurs for very low output signals. Effectively, this means we are wasting the most energy when dealing with these realistic listening levels. We are not using the full 90% efficiency of the Class D amplifier, but we are driving small signals where we have much lower efficiency. So at MPS Axign, we want to address this. Both the switching losses and ripple losses are addressed with one solution, and we call this zero common mode switching. Now, this type of driving and output stage requires some explanation. So on the top right, we see how a conventional bridge-side load is driven using a Class D amplifier. Let's say we have one speaker terminal, let's say the positive V+, and one negative speaker terminal V-. Typically, in a Class D audio power stage, we drive a sine wave on one side and the same sine wave in antiphase on the other side. The resulting differential mode signal can be seen here in blue. We make twice the voltage swing, and potentially we can get 4 times the output power this way. We're using a single voltage supply, and as a result, the common mode, so let's say the average output voltage between the 2 terminals is half of the power supply. So for the sake of this example, we have taken 40 volt as a power supply. However, zero common mode switching, how we do it at MPS Axign, is completely different. Instead of driving two sine waves in antiphase, we drive only one side of the amplifier. So we see that here. One side of the load goes up and comes back to zero, while the other side is stuck at zero. And this means only one side of the load is switching. So we are reducing the switching losses drastically, pretty much by half. If we're switching like this, the effective differential mode waveform, so effectively what we are hearing, is still the same signal. Note that the blue signal, the differential mode output, is the same between traditional driving and zero common mode. However, the big difference is how the common mode voltage behaves. In our case, the common mode is always the minimum possible value. And when driving very small signals, or when driving no signal at all, the common mode level will be zero, hence the name zero common mode switching. So why does this make sense? For this, we have to look at the ripple currents when driving small signals. On the left, we see again the traditional case. So when not driving anything, we are typically switching at 50% duty cycle. So here we see the PWM node going up and down 50%. And as a result, we have this ripple current that runs through the power stage and the output filter inductor. Again, we are wasting a lot of power here while not driving any audio to the speaker load. For the zero common mode switching, however, the common mode is pretty much zero. We have 0 volt everywhere. And we are making tiny pulses as a result. And with these tiny pulses, we also have a very low ripple current. So by driving it this way, we end up with the same differential mode output voltage, but we reduce the ripple losses drastically, and we reduce the switching losses by only switching one side at a time. So this sounds very attractive, but why doesn't everyone drive the power stage like this? Traditionally, driving your power stage like this causes significant crossover distortion, and we can see that over here. Where I've made the red circles, we have a very sharp knee point, where let's say the waveform turns into a flat line. Typically, without any feedback, we would see some ringing here, and we have a lot of resulting distortion. However, as mentioned before, we can suppress distortion in the audio band by using an aggressive loop filter with high loop gain. So even driving it very efficiently, we can still reach a THD plus N well below 0.005%. And here on the right, that is shown. This is our total harmonic distortion plus noise ratio over frequency. And this is using our most efficient system. Note that it's frequency independent. We do not have an increase in distortion for higher frequencies, like you sometimes see. And we have a load independent performance. In short, we are combining extremely low losses with high audio quality without compromising. So besides the high efficiency, let's move on to the audio quality. In particular, I want to first talk about the distortion, because when we ask what determines high audio quality, we have to address the distortion. Without getting into the technicalities, the distortion can be described as that oof feeling you get at high volumes when someone cranks up the volume. The human ear is incredibly sensitive to distortion. The way a bad amplifier can distort your audio signal is not a natural phenomenon. And a big role in the distortion is played by the output filter inductors. And that is why post-filter feedback that can correct for distortion in the output inductors is such a good idea. MPS Axign's feedback loop has tight control at all output levels, and that is seen in the top right. So here we drive an output stage from 5 milliwatts up to 30 watts. So this is a typical output power range, for example, a smart speaker or a small Bluetooth speaker. And we can see in blue for Axign that we have a consistently low distortion figure. And in green and in red, we see two of our most popular competitor solutions, and around 1 watt, say a very typical listening level for a small smart speaker, we have 33 times lower distortion. Now that's not all. The low THD is throughout the entire audio band. So we see that here on the right. Independent of frequency, the THD plus N stays extremely low, where at competitors sometimes you see that it goes up for higher frequencies. And we can also realize this with a large variety of power stages. Here I've made curves for 2 of our integrated power stage solutions and 3 of our discrete power stage solutions. And we can see that despite there being small difference in power stage performance, we have consistently excellent performance. Now, besides the distortion, we have to talk about the frequency response as a key indicator of good audio quality. So the MPS Axign technology also creates an extremely flat frequency response with minimal phase shift in the audio band, all thanks to the feedback loop. So on the left, we see a measurement of a typical system using our post-filter feedback. And we see that the frequency response is extremely flat, up to 20 kilohertz, independent of load. One curve with 4 ohm, one curve with no load attached. There is less than 0.1 dB of variation in the audio band. However, at competitor solutions, we don't have the post-filter feedback, so the load can strongly influence the LC filter response. And what this means is that for, say, a 2 or 4 ohm load, we can have significant droop, an overdamped response, shown by the green line. So we might already lose a lot of gain in the high frequencies and have a lot of phase shift. And for an open load, we might see a lot of peaking. And all these artifacts are suppressed by having post-filter feedback. As a result, with such a flat frequency response, we get the customer feedback that there's no smearing of the sound, and the instruments are distinct and precise. Now, having addressed the high efficiency, power driving, and the audio quality, we have to also talk about cost-effective solutions. So using one of our MPS Axign technology reference designs, you can typically go to heat-sinkless designs. And this is really proven in practice. So on the right, we see one of our designs with a 500 watt GAN amplifier. This is 2 times 500 watts without a heatsink. So by using such technology, you can also lower your total BOM cost by removing heatsinks, but also by removing fans from the enclosure. Furthermore, you have no constraint on the inductor performance. This is because the distortion is corrected by the feedback loop. And this gives the designer a lot of design freedom. Perhaps you can pick a lower cost inductor with higher distortion because it doesn't matter for the overall system performance. As mentioned before, the Axign controllers are power stage agnostic, which means that very cheap parts can be used for the power stage, including some motor drivers. Typically, one of the issues can be that there's high dead time here, or a low performance power stage with a lot of noise. But again, these are no issue due to the feedback principles. And finally, we have very low power supply requirements. The feedback loop also provides an extremely high power supply rejection ratio, which means that the constraints and requirements on your power stage are more relaxed. So, to summarize, with traditional amplifier solutions, audio designers are forced to choose 2. You could make a high audio quality system with high efficiency, but you probably end up with a very expensive system. Or you could go for a very cheap and high audio quality system, but probably have a lot of power losses. Or you could go for a very efficient and low cost solution, but as a result, the distortion will be incredibly high. So at MPS Axign and our post-filter feedback, we say audio designers can achieve all 3. The quality is ensured by the feedback loop because we are compensating for distortion introduced by the output filters, and we are load independent, which gives us a flat frequency response from DC up to 40 kilohertz. So we can also support high-res audio. THD plus N numbers well below 0.005% are achievable using this technology, even with cheap components. We achieve high efficiency using our zero common mode operation, and this addresses the switching losses and the ripple losses. And this is ideal for realistic audio levels. And finally, we aim to create a low system cost by eliminating heatsinks and fans, by enabling use of low-cost nonlinear inductors, and we give an easy choice for power stage and power supply. To summarize the whole story, we take a fully digital feedback loop as a starting point because it has distinct advantages over analog feedback loops. It is configurable and programmable, and we don't suffer from component spread. The MPS Axign technology is built on patented ADC and mixed signal expertise, and this is what enables the best audio feedback loops. Again, the quality of your feedback loop is determined by the quality of your feedback path. The zero common mode operation drastically reduces the power losses. The ripple currents are drastically reduced at realistic listening levels, and the switching losses are reduced by only switching one side at a time. The noise and distortion in the audio band are suppressed by a high-order feedback loop, and we have an extremely flat and load-independent frequency response due to the post-filter feedback. In short, highest audio quality and the lowest power losses, and a cost-effective solution, no compromise. Now to finish up, I would like to point out we have another webinar coming up, our MPS Axign Class D Technology Deep Dive. If you're interested in our technology and want to learn more about what's under the hood of our chips, please subscribe to our next webinar. For now, I propose we move on to the Q&A. Thank you.
Thank you, Olaf. Now, if anyone has any questions, please use the QA button located at the bottom of the Zoom meeting interface, and we will answer them live. One of our most asked questions is if the session is being recorded. Yes, it is being recorded, and the recording with the presentation will be sent out to all registrants and be posted on our website within the next couple of days. All right, looks like we have one question to start off with. Let's see. THX is offering amplifier technologies achieving better than 0.001 THD and 135 dB dynamic range. When will we see this from MPS?
All right. So I think we're just addressing the performance specs here. So where really the value proposition of this MPS Axign technology comes in is that you can get these very high performance numbers at a very low cost and also a very low power dissipation. So it really brings the whole picture. So it's not per se about having the highest possible audio performance, especially for like, let's say, hi-fi solutions. It's really about bringing the total package.
Thank you. Next question. You mentioned that MPS Axign controllers can work with different power stages. Can I also use a single Axign controller with multiple different power stages?
So that's a very good question. As I mentioned, the controllers are what we call power stage agnostic. So they don't care about which power stage we are using. So it is possible to, for example, take a 4-channel controller and use two-channel power stages behind it of a different type. You could even take 2 different supply lines and use one lower power, lower supply line power stage to make 2 tweeter channels, and use one higher supply line and a bigger power stage to make 2 woofer channels. So you could certainly combine those with a single Axign controller.
Thank you. Next question is, what is the power level of your Class C with post-filter feedback?
So I think we are referring to the output power level here. So that's the beauty of it. Because we are power stage agnostic, we can in principle use any type of power stage, which will determine the eventual output power. So for example, the MP8049S power stage, we typically use to make 25 watts to 50 watt applications. But we can also, for example, make a discrete GaN solution where we can go up to a 500 watt channel. So based on the choice of power stage, we can address all output powers with the same Axign controller.
Thank you. Next question, when will a reference design or evaluation board be available online?
Yeah, so we are working very hard as part of MPS to make these reference designs available to a broader audience. I hope to post some reference designs very soon online. And the best way to keep up to date is by subscribing on the website and get notified as soon as something comes online. We really have to think in an order of magnitude of a couple weeks.
Thank you. Next question, does the design with 2 chips require more PCB space for components comparing to the traditional Class D amplifier design?
So that's a good question. So indeed, we are using a distinct controller and a distinct power stage, in contrast to having one integrated power stage. So it might be slightly and just so slightly larger in the small output powers, say for a 25-watt application where we see a lot of integrated power stages. But at higher output powers, typically we have to separate these packages anyway, and then we are not larger. Also, if you take a multi-channel application, so one controller and 4 power stages, for example, it's not per se bigger than having 4 integrated devices. Also looking at the PCB overall, I think the output inductors, for example, are very influential on the total PCB area used. So relatively speaking, the Axign controller does not add a lot to the PCB area.
Thank you. Next question. When using Class D amplifiers, one common complaint is dead time distortion in the power stage. Class B does not have this issue. Do you see this issue as well in Axign solutions?
Right. So dead time distortion is often addressed as one of the issues in Class D, that we have a trade-off there between adding dead time for higher efficiency, but at the expense of performance. But this is really one of the issues that our post-filter feedback can address. Sometimes we use higher dead time because it gives very power efficient solutions, but we don't see the distortion back in the system level performance because the feedback loop is able to suppress it. So dead time distortion is not an issue for this type of system topology.
Thank you. It looks like we have one more question. I want to try an MPS Axign amplifier with my current DSP front end, but I don't want to change my I2S output format. Can MPS Axign products support different formats of I2S?
Yeah, that's an excellent question. So very often customers already have a existing DSP front end. They have their own system on chip and they don't want to change that. They just want to change out their amplifier solution for something with lower power consumption or higher performance, something that MPS Axign can provide. So our I2S formatting is completely configurable. We can in principle interface with any DSP or SoC that you put in front of it. We support I2S formatting, but also TDM. So if you want to make a 4-channel amplifier, you can supply a TDM4 format.
Thank you. And that seems to be our last question. However, I will hold here for a few more seconds. If anyone has any other questions, please type them into the Q&A section of the Zoom meeting interface now, and we will answer them live. All right, we got one more. Will the chips be available via Mauser in the near future?
And that is a good question. I'm not entirely sure. I think the best way to go about it is to use the Monolithic Power website.
Sounds good. All right, that looks like it was all of our questions for today. Thank you again, everyone, for joining us, and we look forward to seeing you at future sessions.